So, the chain rule, and I don't think you need to write this down, okay? But there are still some functions that we would not be able to take the derivative of, okay? Or there are times where we maybe don't want to go through the algebra to be able to take the derivatives, okay? What I want you to write down from this slide is that our chain rule is going to be used on composite functions. Can somebody give me an example of the composition of two functions? Yes?
Would that be like the original function and then f?
No, because you're thinking of separate. I'm thinking of two functions composed together. It is. Okay. F of g of x is a composition. You have a specific example for us?
Well, I was going to say like x plus 2 quantity squared.
Okay, so technically, x plus 2, the quantity squared, we have a linear inside of a quadratic, right? X plus 2 is inside of our squared, okay? Pretty simple one, okay? What's another composition function? Maybe a little bit more juicy. Not that that was a bad example, it's just very basic.
Rational? Like irrational? Like x, I don't know. X squared minus 2 over x minus 2.
So that, I mean, technically, yes, that would be a composition function. We see that, and a lot of us say, ooh, cool, the product rule, or the quotient rule, right? The one that Pierce gave us, a lot of us are seeing, oh, we can multiply that out and then take the derivative. But what if we had, like, sine of 5x plus 2 cubed? That's what you're going to say? Okay, that's a pretty intense composition. Okay, how are we going to take that derivative? Okay, the chain rule. Even the sine of 5x, that is a composition. 5x is inside of sine. Okay, we need to know how to take the derivative. Now, nothing that we've learned before is going to be like out the window, okay? We still have to incorporate the product rule, the power rule, the quotient rule, all of our trig derivatives that you remember and have memorized, right?
Yep. Yes.
Okay. So, don't write this down. Don't write it down. If f is differentiable and g is differentiable, then our composite is differentiable. And this, ladies and gentlemen, is our chain rule. Please write it down. I just don't think in your notes you need to write that f and g are both differentiable. So we take the derivative of the outside function, leave the inside function alone, times the derivative of the inside function. Okay. Derivative of the outside where the inside stays, times the derivative of that inside. You have to practice this. It looks simple as I write it up here. But every composition is different. Okay? Our process for the derivative is the same, but composition functions aren't created equal. Some of them are going to be really easy to derive. Some of them are going to be pretty complicated. If you do not practice, you will not get the hang of this. And Thursday is going to be a disaster for you. I'll just be very straightforward. Okay? This week is not the week to choose to skip your homework. Okay? Now, don't worry about writing this down. I just want to kind of prove to you why this is the chain rule. Okay? So let's say that y is a function of u. Okay? And u, this guy inside, is a function of x. Okay? Well, when we take this derivative, we would say the derivative of y with respect to u. We take this derivative, we're talking about the derivative of u with respect to x. Okay, the derivative of y with respect to u, dy du. The derivative of u with respect to x, du dx. What happens when we multiply these together? And we're left with dy dx. Okay, which is what we are wanting to find. This is the chain rule. Okay? I'm never going to ask you to regurgitate this, but I know that there are some of you in here who really like knowing where things come from. This is where it's coming from. Okay? All we're doing today in class, and all you're doing for your homework, is practicing how to use this chain rule. Okay? So we're literally going to have example after example after example. Okay? No new concepts besides that right there. So, please, write this down. Okay? Up until today, this is a problem we would not be able to do. There is no other strategy we can use to take this derivative other than the chain rule. So, do we have a composition of functions?
Yes.
Yes. We have a quadratic inside of cosine. What is our outside function? Okay, cosine is our outside function. X squared plus 9 is our inside function. Okay. So when we take the derivative, we are going to take the derivative of our outside. What's the derivative of cosine? Okay, so the derivative of our outside function is negative sine. Inside of sine, we leave it alone, x squared plus 9. Then we have to go inside whatever that function is and take the derivative. Okay, what is our inside derivative? Okay, our inside is x squared plus 9. Its derivative is 2x. Some of you are a little bit, some of you like to be more organized than others. I accept this answer. There's nothing wrong with this. But some of you, this bothers, and you want to change it to negative 2x sine of x squared plus 9. I have no problem with that. Either answer is fine. Some of you like to reorganize things. Some of you don't care. Okay, I get it if you like to reorganize things. I just want you to understand that 2x has nothing to do with the angle of sine. And that's the chain rule. Okay? Like I said, not all compositions are created equal. Okay? Let's try another trig one. Well, some of us need some practice with trig. Okay? This problem's pretty similar, isn't it? How about you take the derivative and compare it to your neighbors? See how it goes.
I think we should just like stop at problem and then take a quiz.
Okay.
Yeah.
You're done. Alex, what's our derivative?
2 cosine 2x.
2 cosine of 2x. So the derivative of sine is cosine, we leave 2x inside, times the derivative of our inside is 2. Very nice. Okay? Alright, let's maybe like step it up a notch, right?
I'm good at this now.
I know you like that notch, but
I don't know.
I'm not saying you have to know how to take this derivative right now. I'm going to walk you through it.
I can't find the
Ah. Our outside function is the radical. Inside the radical is 5 minus 3x. Now, do we know how to take the derivative of a radical? We know how to take the derivative of something to the 1/2 power. So I would encourage you to write this as 5 minus 3x to the 1/2. 5 minus 3x is inside of our radical, which is considered to be our outside function. Okay, so what we can do for our derivative, our outside function is something to the 1/2 power. Well, we know if we have that 1/2 power, we can use the power rule. So we're going to use the power rule where our inside remains as 5 minus 3x. So I took that power, threw it out in front, and subtracted the power by 1. Are you good with that? Then, what's the derivative of the inside? -3. I'm happy, totally happy with you leaving it like this. I'm also happy with -3/2 times 5 minus 3x to the -1/2. Either one is fine. They're both appropriate. Questions on that example? Okay, I'm going to refer back to your quiz quite a bit on your quiz from last week. There was a quiz question last week. Two x plus, well, maybe I should put y equals, huh? 2x plus 4 to the 2nd power. How did you do it last week? Multiplied it all out, and then you could use the power rule. Okay? That's not your only option right now. Okay? You can view this as a composition. Okay? This is very similar to the composition that Pierce gave for an example. Okay? This is a composition. We can treat it as such. Write down what you think the derivative of this is, based on the chain rule. Compare it to your neighbors. Trenton, what do you have for us?
2 times 2x plus 4.
Like that? What do you think? Okay, so we do the power rule. Our exponent goes to 1. And then inside, we have to take that derivative to be 2. Now, if I ask you where this function has a horizontal tangent line, that's a pretty nice derivative to set equal to 0. I can tell you right now that x equals -2 without a whole lot of work. Right? Okay. This is not the one I want to do. I'm going to change it. I'm pulling an audible. Sometimes I do that. What? It's like almost exactly like the one we did. Oh, the scribbles. Oh. Okay, when we get into these trig chain rules, we have to be very careful with what's the outside and what's the inside function. What is the inside function? Well, x is inside of tangent, where tangent is inside of a square, right? I know, because the derivative of x is 1. So it's really just a normal chain. Okay? If that were to be like 5x instead, then it would be. Can we do that? We can. We're going to do that tomorrow. Yeah, that's too much. That's too much right now. Okay, this is the equivalent of the tangent of x, the quantity squared, but we write it like this, right? If you need to write it like this to have your brain click with the chain rule, I have no problem with that, okay? But we need to understand that tangent is inside of the square. So when we take the derivative, our first job is going to be the power rule. Whoops. Our first job is the power rule. Keep the inside the same. Times the derivative of tangent is secant squared.
I just kind of went to like divide those two.
Okay, write it down. Write it down. No problem. Don't do anything yet, but talk to your pod about the process we would have to take. What do we have?
Power rule. And deposit times. Yeah, chain rule on the first one. But then I think it's more on the
So you have to do like you have to like the chain rule for the secant x, and then you also have to do like the product for the other one.
Okay, what do we have going on up here? Okay, we have two functions being multiplied together. So we have a product rule. But inside of our product rule, we have a composition. Do you see that? How it's a composition times tangent? So we are going to have to do derivative normal plus normal times derivative, right? Okay, let's put in our normal functions real quick. Normal and normal. Okay. Now let's go ahead and take our derivatives. Okay? Let's start easy. What's the derivative of tangent? Okay. Better. So now when we take the derivative here, we're going to have to do the product rule times the derivative of secant is secant tangent. I didn't leave myself enough room, sorry. Okay, so power rule, the 3 came out in front, changed to a square, times the derivative of our inside function secant is secant x tangent x. Okay. Do you understand why I'm saying you have to practice this?
Yeah.
Okay. Every problem is different. Okay. Allie. Uh-huh. That's why the derivative of tangent over here is secant squared x.
Well, I know. I was just thinking it was tangent squared, or tangent x, secant x, tangent squared x.
Okay, yeah. The derivative of tangent is just plain old secant squared x. Is that what you're asking?
Yeah.
Yes.
But then why is it secant squared x? Yeah.
Okay.
You're
Okay. Okay, we're on the same page. Okay. And see, and that's why it's important. And I know we're still like learning our trig derivatives, but if we don't know off the top of our head our trig derivatives, this problem sucks. I mean, there's no other way to put it. Okay? By Wednesday, please have your trig derivatives down. Like, you don't have to go back and look at them. That'll help our review.
Okay, also, what if you do, when you do the chain rule for secant cubed of x, wouldn't it be 3 secant squared? Never mind.
Okay. Okay. It's clicking. Oh, look at all these that I made slides for and I just did on my own. Okay. I'm not going to do that one. Let's go to this one. I'm picking and choosing here.
Why is it capital?
Yeah, I don't know. Something different. You don't have to write this capital G.
Just want to make sure.
You can name it E of X if you want. E for Lee or something like that. All right.
To the 7th.
To the 7th.
Who said that?
Okay. Turn to each other. Don't do any work. What's our process?
So the chain rule, and then the quotient on the other top.
Yes.
So it would look like 7 to that whole quotient to the 6th power times the quotient.
Ethan, what do we got going on?
So you have to do 7 times that whole unit to the 6th power time. So yeah, we'd have to do the chain rule times the quotient rule.
Okay, so we have a chain rule problem, right? We have that function inside of the 7th power, right? So we're going to have to do the chain rule to where we are saying 7 times this ugly guy to the 6th power times derivative of the inside. What are we going to have to use for the inside derivative? Okay, quotient rules. I'm going to put some parentheses here. Derivative of the numerator times the denominator minus our numerator times the derivative of our denominator all over denominator squared. Ta-da! I will lay it like that. Okay? That sounded like your voice, but very similar to
This is the answer.
Okay, I have one more example. One more example. Write it down. Discuss the process without doing work. This is nothing compared to what we'll do tomorrow, so. Baby steps, baby steps. What about Bob? What do you mean? No one really quotes. I am not.
So first chain rule.
then power.
I feel like males are like programmed.
Yeah, the inside is
that.
power rule. Well, the one would just disappear.
Or maybe they like care more. I don't know, but I feel like I know a lot of things.
Yeah, I like moving quotes, but I have no idea how to do that. Okay, fine.
Cool. Okay, so our process. Julia, what do you think?
Yes.
Okay, so we have a composition where our outside I think I'm talking
Sorry.
and waving my hands. Okay, we have a composition where our outside function is a power. And then Julia says inside we have a product. Do you see that? X to the fifth times cotangent. So, when we take our derivative, for our chain rule, our outside function is a power, so we will work on our power rule. Ooh, when I subtract one power, what do we get? -9. Okay. Times the derivative of the inside. Well, the derivative of 1 is 0. I'm not going to write it. Plus, we have a product. So we need to take the derivative of x to the fifth times cotangent of x plus x to the fifth. What's the derivative of cotangent?
Negative cotangent x.
Negative cosecant.
Negative cosecant squared. You just rattled off the derivative of cosecant.
Yeah.
Yes.
Okay, why aren't you writing 0? Because wouldn't it eliminate yourself?
Because it'd be 0 plus. Like it's 1 plus this, so it'd be 0 plus this, and anything plus 0. Like if it was being multiplied, that's going to 0 off some stuff, but if we're just adding, we can just drop it.
Do you believe we might have to solve?
Like if I had 4x squared plus 5, our derivative we just write as 8x. We don't write 8x.
Yeah, don't worry.
So this right here is a product.
Because you do
So I'm using the product rule. Derivative of the first times the second plus the first times the derivative of the other. Yes, no. Do you want me to talk through it again? Okay. So here's the deal. I imagine your homework is going to start pretty soft, okay, with some more simpler ones. And as you go through your homework, they might get a little bit more complicated. Really take a step back and think, what is going on here? Is it a composition? What's inside, what's outside, okay? If it's not a composition, you don't need the chain rule, okay? But really think to yourself, is it a composition? What's inside, what's outside? And then maybe if you have something inside that has to require another rule, you kind of have to process that too, okay? How important is your homework tonight?
Very.
So important, okay? Somebody asked me about, will we ever have three functions composed together? Those are the examples I want to go through tomorrow. Yes. For 2 minutes.